Hello everyone. Today we will be discussing creating more efficient solar cells by bonding gallium arsenide to silicon into tandem solar cells using nanobonding and surface energy engineering. My name is Pranav Penmatcha
My name is Siddarth Jandhyala.
and these are our co-authors and faculty members. Solar cells are the new gold standard in renewable technology. However, there are currently two main problems with creating highly efficient tandem solar cells by bonding gallium arsenide to silicon. Native oxides nucleating in wafer surfaces and extremely high temperatures required to bond both the wafers together, causing thermal expansion and crystal defects on the wafer. Our main methodology is nanobonding, which involves three main steps. Surface energy engineering, or SEE, in which we put the wafers in far from equilibrium states by etching native oxides off the wafers, nanocontacting, in which we make mechanical contact at the nanoscale, and bonding activation, in which we apply radiation to bond the two wafers together. SEE aims to etch the native oxides off the wafers while keeping the structure using dilute hydrofluoric acid on boron-doped silicon wafers and aqueous ammonium hydroxide on tellurium-doped gallium arsenide wafers. This is to preserve the structural integrity of the wafers. The etched surface is also terminated or passivated to avoid re-oxidation. We will measure the results with three characterizations for SEE: the three liquid contact angle analysis, or 3 LCAA, X-ray photoelectron spectroscopy, or XPS, and ion beam analysis, or IBA, and the two characterizations of nanobonding, which are surface acoustic wave microscopy, SAM, and cross-section transmission electron microscopy, or TEM. The first characterization of SEE is three liquid contact angle analysis, or 3 LCAA. With 3 LCAA, we can measure the surface energy of the wafers by using the contact angles of the three liquids, water, glycerin, and alpha bromonaphthalene, which correlate to the three parts of the Van Osgood-Chaudhary theorem to measure the total surface energy using the Lifshitz-van der Waals energies, electron donor energies, and electron acceptor energies. The second characterization is X-ray photoelectron spectroscopy, or XPS, used in order to measure the surface chemistry of the wafers. The 1.5 kilovolt X-ray beam excites valence electrons on the surface, which are then measured by the electrostatic analyzer, or ESA, to measure the binding energy in the atoms. With the electron binding energy, we can see the percent oxidized gallium and the ratio of arsenic pentoxide to arsenic trioxide. The third characterization is ion beam analysis, or IBA, which is used to measure the oxygen coverage of the two wafers. In IBA, alpha particles backscatter elastically to provide a corresponding measurement for mass. When it is paired with 111 channeling and nuclear resonance, the data is a lot more accurate, and it shows that there is a signal to noise ratio increase in oxygen by 600.
So what did we find? 3 LCAA revealed that we successfully put the wafers in far from equilibrium states, with gallium arsenide going from strongly hydrophobic to hydrophilic, and silicon going from strongly hydrophilic to very hydrophobic. IBA revealed that total oxygen coverage decreased by approximately 12% on silicon and approximately 49% on the gallium arsenide wafer. However, we also found that the ratio of gallium to arsenide remained 1:1, showing that we kept the structural integrity of the wafer. Finally, XPS revealed that gallium was 2 times more oxidized than arsenic, and the number of arsenic pentoxides decreased by 13.5%, but the number of arsenic trioxides increased by 13.5%, causing the wafers to enter highly oxidative states. This means that we were successfully able to put the wafers in far from equilibrium states, priming them for nanobonding. XPS also revealed that carbon contamination affected the surface composition by less than 10%, meaning that the extraneous carbon did not interfere with the results from our experiment. Additionally, there are two characterizations for nanobonding, which are surface acoustic wave microscopy, or SAM, and cross-section transmission electron microscopy, or TEM. TEM allows us to image the gallium arsenide to silicon interface, and this is coupled with SAM, which images the bonded area of gallium arsenide to silicon and quantifies the percent of surface area bonded. Furthermore, SAM reveals the defects in the bonded interface. The results for nanobonding are as follows. Firstly, SAM revealed that 98% of the gallium arsenide wafer was successfully nanocontacted and bonded to silicon with 60 kilopascals of compression. But even more importantly, SAM quantified that 48% of the gallium arsenide wafer was successfully nanocontacted and bonded to silicon without compression. This confirms our hypothesis that we are successfully able to bond gallium arsenide to silicon at temperatures below 220 degrees Celsius. However, the white area within the black contour indicated by the large gray arrow depicts particulate defects in the interface. This is due to particulates interfering with the scan, so we can conclude that we need a class 10 ISO 4 particulate control to conduct nanobonding. In accordance with the data from this experiment, we constructed a ball and stick model of the gallium arsenide wafer both before SEE and etching and after SEE. Though the decrease in gallium trioxide and arsenic pentoxide is subtle, it corresponds with the complete reversal in hydroaffinity from gallium arsenide being initially hydrophobic to being very hydrophilic in accordance with our hypothesis. In conclusion, we confirmed our hypothesis that SEE can put the wafers in far from equilibrium states and modify their surface energies. Secondly, we found through IBA that oxygen coverage decreased by approximately 12% and 49% on the silicon and gallium arsenide wafers respectively, while keeping the structural integrity of the wafers. Furthermore, XPS revealed that the number of arsenic pentoxides decreased by 13.5%, but the number of arsenic trioxides increased by 13.5%. And although it is a subtle difference, it corresponds with a complete reversal in hydroaffinity of the gallium arsenide wafer. From SAM, we found that 98% of the gallium arsenide wafer was bonded to silicon without compression, but with compression, but 48% of the gallium arsenide wafer was bonded to silicon without compression, showing that nanobonding is able to successfully bond gallium arsenide to silicon at temperatures below 220 degrees Celsius. Finally, TEM revealed that there was about 10 nanometers of oxidation, showing that both wafers are highly reactive after SEE. These are the references we used, and thank you for your time.